and make them become one of the leader of the software-defined vehicle movement. So please, with me, welcome on stage William Wei.
Hi, good afternoon. Welcome everybody. I just flew in a few days ago from Taipei. I'm now based out of Taipei, the center hub of AI SoC island. Little bit about myself. I started out, I joined a company called Next, which I met the founder, which is Steve Jobs, back in MIT in my graduate school. And I remember I spent my tuition $6,000 to him on the MIT bookstore. And then he introduced me about what he's doing about Next. He just came out of Apple, and Next is the machine his dream machine that he's gonna transform for decades. And I didn't know him, right? A kid from Taiwan. So I bought his computer, I put it in my lab, and all my lab mates, they're using Sun Microsystem, and I'm using Next workstation. So at that time, we enjoy using Next. We enjoy early internet in the campus, and then that led to Next led to the first internet browser, which is called World Wide Web browser. And then Mark Andreessen created World Wide Web, and then when he came back to US from CERN, he created a Netscape. I don't know if you old enough to remember $15 Netscape. That's the era that I live in. And so after that, we experienced some downturn because it's too expensive, that machine, compared to PC. But compared to workstation, it's very cheap, $6,000. And then one day, 1997, Steve Jobs came back to us, to Redwood City. We were based out of Redwood City. Say, hey, guys, you guys don't have to quit, because some company bought us. And we were thinking, oh, probably IBM, yeah. And he said, it's Apple. So we were disappointed at that time because Apple was dying. But when we go to Apple, things start changing again, because the senior VP engineer got fired, CTO got fired. So all our colleagues become working on this computer on your pocket. It wasn't called iPhone, but computer in your pocket. That's the goal, 10 years ahead, 1997. So after 10 years, 2007, when Steve put on this, it's a browser in your pocket, it's an iPod in a pocket, it's everything in a pocket, it's a software defined. That used to be a hardware, and you can put it in this software defined thing in your pocket. It's called iPhone, but it's nothing about the phone. So today's topic is automotive. But I'm not gonna talk about automotive. I'm talking about future of this computer that is greater than your pocket of the iPhone, the computation power, the battery power, everything. It's perfect for computer science or system engineer to go flitter around about what we can imagine. So let me just jump right in while you're taking your nice meal. Let me see. Okay. Okay, so basically I just mentioned, at that time, Netscape, so web first. So at that time, every company want to become internet company, they have to build a website, right? That's called web first. All the business conduct from the web, right? And then you remember when the iPhone introduced is the beginning of mobile first, right? Everybody want the app. So you go all the resource channel to your app on your mobile phone. And today we are experiencing AI first, right? We are looking into the future, spending a lot of money, doesn't know when to get the ROI, but people still piling a huge amount of money and energy into AI. That remind me of year 2000 when I was in the Valley. The internet of building, everybody was thinking about what is internet for. It's a bulletin board like Yahoo, put all the directory on you. Is that internet? Nobody can imagine today how people use internet, right? And at that time, only Cisco make money. Cisco is like today's AI NVIDIA, because all San Jose is all Cisco's campus. Cisco is everywhere. Today, NVIDIA is everywhere, right? Sorry. Wrong direction. Okay. So if we're talking about AI, we're talking about like AI started out probably 15 years ago. People in automotive know they run AI. They care about TOP. TOP means trillion operation per second process. Why do they need TOP? Why do they competing like, okay, we have 100 TOP? Because it's based on the model called convolutional model. Convolutional model in AI is this special field, try to do object detection, try to do object classification, try to do all this intermediate, nothing about driving, right? Object detection has nothing about driving. Scanning your environment is nothing about driving, right? So adding RNN. So about 8 years ago, come out with a paper called Attention is All You Need. That's the baseline of transformer today. Transformer is the architecture behind ChatGPT, behind LLM, large language model. So transformer become really famous all of a sudden because ChatGPT. But moving on to transformer architecture, vision transformer come along, and by the performance in terms of object detection using vision transformer architecture, it kind of kill convolutional model. The accuracy rate and the performance is great today. So transformer is eating everybody else right now. So let's move on to the center of what a transformer application called large language model. So transformer is an architecture, but LLM is a model called large language model who power ChatGPT. Okay, so that's so LLM become the OS in AI. That's this term is coined by the leader of AI, co-founder of OpenAI, Andre Kapasi. Right? Recently, he keep talking about. He is also the one who created autopilot in software stack in Tesla. So why OS? Why LLM is OS? Because it's not about language; it's about reasoning. So we have this enter the scene. So everything it's about foundational model. Then we kind of officially enter the model-centric ecosystem. It's not about application. It's about like what model outperform which model every day. Some research lab somewhere say, okay, their model after benchmark, surpass ChatGPT 4.0, something like that, right? It's all about model. And this model-centric ecosystem create this what we call foundational model that is the base of reasoning core of all the generative AI. So we have all this the really crazy smart foundational model and get it smarter. It's called pre-trained LLM, which is GPT, right? Generative pre-trained transformer. And then what we can use is like automotive industry or health industry can use their domain knowledge to continue training, fine-tune this model to become like I would say a foundation model is like you graduate from college, you kind of general knowledge about everything about the world. But this fine-tuned domain model is like a graduate student, right? You're a graduate student in automotive industry. You know everything about automotive. So you fine-tune all this data, become domain LLM. And then for application, you want to say Mercedes-Benz or Volkswagen want to use it in their car. They need to train for their own brand, the Mercedes user experience, everything about this brand. It's called private LLM, only Mercedes use. So this concept is fine-tune and fine-tune based on foundational model. So the process is like this, right? So you have the GTP4, you have Llama 3, which is open source. You have Cloud, you have the Gemini, all these frontier model everybody is excited about. And then you distill them. You kind of ask questions and then distill the data and then fine-tune more domain, using domain data set to train like education. It's about climate, automotive. And then for the application model, you train this, you fine-tune this private LLM, my company LLM, personal LLM, my car LLM, which later I will share with you guys. I am driving a Toyota 2021 RAV4 hybrid, so I fine-tune them to put it in my car. So you have all this leading company, right? Spending a lot of money and energy, resource. And then all industry can start using this foundation model by fine-tuning with domain data. And then from the domain data, you fine-tune again to your private brand data. Now, you use this private pre-trained model, put it in somewhere, your company's cloud or on the car, called on-device car, right? And then you start inferencing. So there's a training stage and then now inferencing stage. Most of what I concern today is about inferencing, and I'll tell you why. So inferencing is about using the pre-trained model. So this is I asked ChatGPT, I give him some private data. I asked ChatGPT to analyze and then project the energy consumption trend for global model. So the training is actually it's growing, but kind of slowing pace because the chip become more efficient, but the scaling law continue. So it's a steady growing in terms of consumption, and then fine-tuning, the next step, fine-tuning, because everybody, the community will be bigger than the foundational model community. So you start fine-tuning for your domain. But for inferencing, it's gonna consume more and more because when people start using it, when killing app getting invented, everybody's gonna do inferencing. Most people is not doing training, just inferencing. And then because this, we need to design domain-specific architecture for hardware. So hardware getting more specialized. Like Jensen once say, we are in the acceleration business, right? So we know Intel CPU, this is like general list of process unit. It basically can do anything. Inferencing, training, but it's really, really inefficient. So you come along, GPU is really good for training purpose. But it's not that efficient in inferencing because training, you need to modify the way and do a bad propagation, but a lot of things happen in there. And then you have GPA, right, to simulate whatever the future ASIC, the application-specific IC want to be. Give you an example, when blockchain was in its high, in the hype day, so everybody was mining, right? So people start using, at the very beginning, people use CPU to mine. But when GPU come along, nobody use CPU because you all compete. Now, today, nobody use GPU to mine Bitcoin. Everybody using ASIC chip, right? So the same way is gonna happen for the AI. Google is the first one who come up with the ASIC chip. It's called Tensor Processing Unit, TPU. And then you have everybody, Qualcomm, you have Apple, you have MTK, the core have NPU, right? The NPU is still more generic, neural network processing unit. You have vision based. But all this is ASIC. So ASIC, when you design ASIC, you need to come up with an application. You have application, then you design a specific hardware, silicon, for that application or for that software stack. So that's why it's called software-defined chip, just like software-defined car, right? So actually, the development is a software-hardware co-design from the compiler knowledge, from the compiler know the scope of runtime, everything, and then compiler will figure out, okay, the PyTorch command compile to machine code, and then if the machine code need to be simulated, that's inefficient. So compiler people can create a specific instruction set, which is non-existent or simulated, and then ASIC will be created for that specific instruction set. So the logic, the first principle is like that. So software hardware co-design, you're gonna see from the next year, I know, I cannot say which company, but next year you're gonna see a lot of ASIC chip coming out because I'm in Taiwan, I'm dealing with those people. Raise a lot of funding. When you tape out a chip, at least you need 24 to 36 months. So when ChatGPT come out and everybody start invest money and then you start designing that, so you need 24 months at least. So I think next year for Q1, Q2, you will see this kind of ASIC chip coming out. So AI chip from the general purpose GPU become LLM focus because LLM is the OS of a future generative AI. So again, general purpose computing, the GPU for AI is called what we call compute bound. Compute bound because the convolutional architecture is really compute intensive, not really data scale intensive. So a lot of computation. So everybody raced to design a chip that like surpass the 100 TOPS and it burn a lot of energy. Now LLM centric computing in this domain is memory bound, meaning memory size is not enough. It's bound by memory size. And if you put in a lot of RAM there, it's bound by the bandwidth of the memory. So you have a lot of startup right now try to solve that problem. Some of the memory called specialty memory is different from RAM. It's faster. It can be packaged bigger. So in an LLM generative AI world, it's not about compute. It's about memory. I know in current automotive industry, we are still in the compute bound mental set because ADAS is always about object detection, and because it's not end-to-end, I'm going to talk about object detection, object classification, all these convolutional network, why they stay this way, and then moving on to transformer, coming to object detection is going to replace all the convolutional model, right? So memory is the concern. So the computer science system engineers started to move compute to data. In the early computer architecture, we move data to the CPU and try to calculate a result. Now, because the speed limitation, we try to move compute to data. So either we reduce data movement or we increase the size and data bandwidth to satisfy the LLM requirement. So when we talk about the, now we have GPU moving to ASIC. We have two inferencing infrastructure. One is cloud-based, which is today everybody uses ChatGPT. Those are cloud-based inferencing. And those are really large model resides in cloud, Amazon or Azure, and mostly proprietary. The frontier model right now is proprietary, but there's some catching up, open source from the Meta Llama 3.1. It become popular. And I give you an example of disruptive the AC application player, like recently Guac chip. It's a language processing unit specific designed for language processing, which is LLM. So Guac is inference-only cloud chip right now in the market. I think a couple of weeks ago, Cerebras came out and say they create a chip that is 2 times of Guac. Guac chip is about 100 and 200 times faster than GPU, the A100. But in automotive industry, we really need some edge on-device inferencing. It's the same thing. Today we use NVIDIA GPU, put it on your car, burning a lot of fuel, energy. In the future, if AC come in, you're gonna have 100 times more efficient inferencing speed. So it can put in more complex LLM, like Llama 3.1, 8 billion parameter, and these class of foundational model is getting smarter. And mostly based out of on-device, mostly based out of open source, Llama 3, Mistral. And it's, I give you an example, Disrupted IC is the company that I advising in Taiwan called SkyMiser. They are a compiler expert. So they come up with some reference design for chip IP for large language model on device for inference only. So let's jump in that application. In AI, we don't call AI app, we call agent, right? So the app in AI is called agent. Everything is an agent. Why? Why is it agent? Because ChatGPT is not agent. Because you talk to ChatGPT, it gives you some answer, right? But it doesn't put the answer into action, right? But agent give you know what to do and just do it. So all this application we call it agent. So this is the typical AI infra, right? You have an AI LLM chip on device, then you put in agent SDK, and then you put in the fine-tune private LLM model, and then you can start inferencing. And all the agents sit above that, do a lot of inferencing to the AI infrastructure layer. So from here, let's jump into automotive. So automotive is pioneered by Tesla, this concept of a software-defined vehicle. People say over the air OTA, but in our field, OTA is by default. We don't talk about OTA. It's born with it. Everything is a continuous update. We live in this kind of environment. For automotive, maybe not, so it kind of stand out. But software-defined vehicle, to me, is this abstraction layer that separates from the hardware. So all the agent or all the future application can implement some user experience without thinking about what kind of hardware, what kind of skateboard that is run on. It can be portable. And a lot of think about this, a lot of investment, like billion-dollar investment, working on to build an application. If you change the skateboard hardware, you need to do it again. That's such a waste of time. But so in our industry, we don't do that, right? We reuse layer of different layer of build up different layer, even internet, right? 7 layer. We don't go change any of the 7 layer. We just build different application on top of it. And software-defined vehicles should be like that, right? So just simple, the layering is like you have a chip, then you have either real-time OS or general-purpose OS. You have middleware, you have service layer, maybe it's a service-oriented architecture, and you have SDK, you have a lot of API independent from the abstraction layer, and then you have EV, what I put in ELM layer, because LLM, it doesn't share much about traditional SDV infrastructure. It basically has its own OS, has its own chip, right? But it can integrate together with SDV. So you have traditional application, you have AI agent, and you have Copilot. Copilot is ADAS, right, or AD. So once you have this abstraction layer, the software-defined vehicle, what is benefit for the industry looking into future is it become the gateway for other disruptive tech force to enter the automotive. Automotive used to be like, okay, we build our technology secretly, and then all the stack is like proprietary. They don't open up. So once you open up all the domain, like for example, battery domain, there's some people like in and out, live and breathe with the battery discharge, all this battery domain knowledge. They don't need to be the OEM. They can jump in, right? Build the best battery management system, for example. So based on this, about 4 years ago, I started Fastcom to initiate this what I call EV Kit SDK, sort of an Android of EV architecture, right? That was 2020, and then Eclipse Foundation called me up, say, hey, we want to start in automotive. I said, great. So we collaborated, and then so I believe Eclipse Foundation. Today I met some Eclipse Foundation. They're doing a really good job. And then Arm, the director of Arm in Sophie, that the person who started out Arm, called me in 2021 and said, hey, we have this spec called Sophie. It's more in IoT, but it's for automotive. Let's collaborate. So we make good friends there. So all this movement, SDV and then the openness of this platform layer come into play. And then from Japan, Autoware Shinpei called me up, say, hey, we have an OpenAD, so Autoware's OpenAD become one of the Fastcom MIH working group, working on like some autonomous driving infrastructure. And today, what I want to talk about on behalf of FPT Automotive is this concept of AI first, SDV. We built SDV for AI first. All application is about AI. So software is eating the world. Mark Anderson, the same guy who invented the Netscape, he talks around this concept of his observation. Software is eating the world, and that was more than 10 years ago. And today, AI is eating software. How do AI eating software? Because AI can write a code. So you don't have code to maintain. Imagine if you don't have code to maintain, is it good or bad? For the test engineer, it's like scratching the head, how do you test? But for the software maintenance cycle, it's not about code anymore. Then it's about training, it's about data, right? You maintain those source of data to train. And so end-to-end learning and end-to-end engineering become popular today. So when it is end-to-end, you pretty much start deleting all your source code. So all the future of agent development become or shift here to end-to-end. For example, autonomous driving. You see the Waymo is really famous for their modular design. And Waymo, the reason they can drive automotive because they put LiDAR, they put so many sensors, make sure that precise, make sure the distance, high definition map. Basic in my mind, they are building a train. They're not building a smart car, they're building a train. And they use a software engineer, a coder, to duct tape all the object detection, control, PID control, everything together to control the car, right? They have perception, they know how to control. And it's human writing the code to control the car to drive. So they build a lot of really good intermediate solution and put it together. But Tesla was like that at the beginning. But since release 12.x, they swap out end-to-end. So basically they start deleting a lot of code, their backend code, start deleting it. By the way, that's the time when Andre Karpathy quit Tesla to back to OpenAI and start his thing. So on the left side, you have multi-sensing, you have fusion, you have perception fusion, you have planning, you have control. All this are coded with a lot of traditional software code, right? But for Tesla, well, this is not an example of Tesla, but it's similar. This is an example that I drive today. A company called Common AI. They have an open source community, and I took their model. I start training. I start doing a lot of things, fiddle around, and I realized their end-to-end model for longitudinal or latitudinal are all becoming end-to-end. So they don't need object detection. So when you bypass object detection, you don't need convolutional model. You don't need top. From the 100 top requirement, you drop to like 2 top. That's enough. But you need to add more memory for the bigger model. So the idea is the 5-second video shooting in, just like human see the 5-second video in, and then inject it to the AI, end-to-end AI model, and come up with a control command, drive the car. Longitudinal, gas or electricity or brake, left and right, and that's it. So it's about training, it's not about writing code. So this is traditional distributed ECU with no brain, but with this pretty, common CAN bus. Then you swap in some brain and infrastructure, and you can control the car. It doesn't matter it's an EV or not EV, hybrid or gas, right? But in between, you need to have this safety module. For example, to control, you cannot shoot a command like have more than a certain amount of torque. Because it's an ADA, so when the torque is like, you needed more torque to turn the car, but the car sense that it's gonna fit. So it warned the human to take control of the car. That's the current situation, right? Tesla is, of course, they have more data, so right now they are smoother. So this alignment and guardrail is the similar situation that ChatGPT faced today. It hallucinates. It tries to come up with something that is not ground truth. But all the end-to-end autonomous driving data are ground truth, are Tesla collecting all the ground truth data, and then they have a simulation, that's the AI train simulator, and then try to train their new model. So the first agent, what I want to introduce is not about driving, it's about reasoning, it's about interface with human, right? It's an AI command center voice agent. It's an in-vehicle LLM fine-tuned for automotive. So we have this infrastructure here. We have the automotive domain LLM, and it's an open architecture for integration with all other smart cabin components, for example, IVI, body domain, battery, you name it, if you open up. And then you can connect this to what I call non-mission critical domain. You can start experience with this. So the AI-first software-defined vehicle built with Gen AI infrastructure, which is the LLM SoC plus automotive LLM, and you fine-tune. First, I fine-tune with the owner's menu and technical menu. So the menu know this specific Toyota, what kind of message and what kind of characteristic, what kind of control that it has. And then you fine-tune to private, Toyota RAV4 LLM. You put it there, and you can start experimenting with it. So the new automotive experience is like LLM plus fine-tuning plus AI agent. So it's like Knight Rider kit, right? The Knight Rider, if here Knight Rider, it must be old. So this is in my car, my neighborhood in Taipei. So one day, let me see. Let's see if the internet works. Okay. Well, internet connection didn't. Here you go. Let's see. Please lock all doors. And it's really hot inside. Please do something.
Locking all doors and setting the climate control to a cooler setting now. Action. Set climate control and lock doors.
Now it spit out the cold
Lock doors.
in the back end.
Climate control, temperature 72.
So this parameter shooting to a canvas. Unfold the back mirror and roll down all windows.
Unfolding the back mirror and rolling down all windows. Action. Parameters, mirrors, position unfold. Windows, position down. All windows true.
Now close all windows and leave the passenger side window open.
Closing all windows except the passenger side window. Action. Adjust windows. Parameters. Windows, position up. All windows except passenger side.
It's raining now. I can't see clearly. I'm just lying to
Turning
you.
on windshield wipers and activating the defogger for clear visibility.
So you decide
Action.
to.
Activate wipers and defogger. Parameters. Wipers on. Defogger on.
Yeah, it started reasoning what to do. Okay, now play some rock music and let's head home. For this one, I didn't integrate to IVI because IVI, there's no API. It's not open.
Navigation to head home. Action. Play music and navigate home. Parameters, music genre, rock. Navigation, destination, home.
But it spit out the code. Later I will show you.
Rolling up all windows. JSON action, adjust windows. Parameters, windows position up, all windows true.
By the way, which side of the car is my gas cap?
If I don't know my car, I rent a car, I ask him.
Is located on the driver's side of the vehicle.
So I fine tune with the owner menu. Owner menu have all the information, right?
Is this car hybrid?
Yes, your Toyota RAV4 Hybrid 2022 is a hybrid vehicle.
And when does it engage electricity to drive in this car?
In your Toyota RAV4 Hybrid, the vehicle automatically engages the electric motor under several conditions to optimize efficiency. 1. During low-speed driving, such as in city traffic or when starting from a stop. 2. When cruising at a
Yeah, so you got the idea. So I tell my okay. So this is the back end. I have all the question that you write down, and then Jason call with action name and then parameter, all this spit out, right? And the last one. This is one of my engineer. I told him like, okay, this is what I built. Go ahead, do your own thing, right? So he did the same thing, like in one day, just one afternoon, he can achieve this. And then the video with this is a different model.
Hey Jarvis, 是不是電腦 all window 閉じる
So he tried to use a Japanese mixed language to communicate.
すべてのウィンドウを閉じました。
Hey Jarvis, please unfold the side mirror and lock the door.
The side mirrors are now unfolded and all doors are locked.
Hey Jarvis, set the fan to 50% and turn on the dome light.
He put out this to just to let you know, like that the fan is
Fans
stronger,
is set
and
to
then the dome
50%
light.
and the dome lights are turned on.
So basically, the reason that they can be like integrated so fast because I define all the API and I ask my engineer to do on his car. And the last slide I want to show you what's happening recently in AI chip, right? You have a lot of you have your Guac chip, raising 60 million, and then they raise 640 million, Testoran, the very famous Jim Keller's company doing RISC-V, they raise 100 million. They raised 200 million, and then another 100 million with Honda and Motor, and all this, and then this is transformer-based inferencing. They haven't let their chip come out yet, but next year it will all come out. So, yeah, I finished my today's sharing. Thank you. Do we have Q&A?
Yes.
Yeah.
Yes. Thank you, William. So I think we're running out of time, but still, I think we can manage to have a couple of questions if you want to ask him right now, or you can catch up with him after the session outdoor somewhere, sipping coffee with him. So please, any question?
Thank you. So great presentation. Thanks, William. I have a question linked to the edge chips then, yeah? So now we see the inefficient NVIDIA chips for like then also